Um, I'm sorry, but we cannot hear anything.
Can you hear us now?
Yes,
Can you see the screen?
not yet. Now we see. At
All
least
right.
I do.
Looks good. Thank you.
And maybe can you guys mute in the audience? Yeah. All right. So as I was saying, I want to thank Kevin and Mel for the invitation and organizing CANT. It's always a pleasure to be here. So I've spoken about primitive sets in previous times I've been here, and this is maybe something like a full circle moment in multiple ways. So I just want to begin with a very simple definition that's self-contained. So we say that a set of integers is primitive if no number divides another. So if the set is just the number one, then any other number is going to be a multiple of one. So we're just going to throw out one, and just consider numbers at least two, where no number divides another. So the canonical example of a primitive set would be the prime number. So no prime divides another. And indeed, this is one of the kind of motivations for this definition in the first place that Erdős initiated. So another nice example to think about is the set of integers in a dyadic interval. Let's say between x and 2x, where we include one of the kind of endpoints and exclude the other endpoint. And so in fact, if we take two numbers that are between x and 2x, that means their ratio is going to be strictly smaller than 2. And so in particular, one cannot be a multiple of another. So this is a very nice way to generate an infinite family of these primitive sets. And so also if a set is primitive, any subset is also primitive. So it has this nice downward property. So we already have an infinite collection of examples. But historically, another very nice example are called the perfect numbers. So recall, from ancient Greece, we say that a number is perfect if it's equal to its sum of proper divisors. So for example, for example, 6 here has proper divisors 1, 2, and 3, and 1 plus 2 plus 3 equals 6. And we say the word proper just to refer to the fact that we're not including 6 itself. We're not including the number itself. And so the first few perfect numbers have been kind of tabulated even since many kind of centuries ago, 6, 28, 496, and so on. And there are famously open questions about perfect numbers. In particular, are there infinitely many of them? Actually, is there even a single perfect number that's odd? So these are some very old questions, which we're not going to get to today. However, there are a number of other interesting and sometimes unexpected results that have to do with primitive sets. And early on in the theory, many people like Chawla, Davenport, and Erdős all kind of studied primitive sets and believed that they were getting very sparse. So in particular, that the set had zero density. And this was in the kind of early 30s, the prevailing belief. However, it came as a very surprising result when in 1934, Besekovich proved that, in fact, there are primitive sets whose upper natural density could get arbitrarily close to 1/2. So in particular, these sets have positive density, positive upper density. And so in particular, his example is to take this dyadic interval and then make a bunch of copies of them in a very sparse way to infinitely often get this kind of close to 1/2 density. Okay, so this was surprising. On the other hand, around the same time in the 1930s, Behrend and Erdős independently showed that the lower density of any primitive set must always be 0. So in particular, maybe occasionally you can get a set having positive density, but also there must always be a subsequence where the set is very sparse. And in fact, in the course of his proof to do this, Erdős showed the stronger statement that the following infinite series converges. So he considered the series 1 over n log n as the numbers n range in a primitive set A. And so this series will occur a lot in this talk, and it goes by the name of these Erdős sums and denoted by f of A. And so Erdős proved that these sums converge uniformly over any choice of primitive set A. So there is some absolute constant in which f of A is always at most this constant. And later, actually, Erdős conjectured that this constant is actually the corresponding sum for the primes. So in particular, that the maximum Erdős sum should be given by the primes. Okay, so the Erdős primitive set conjecture asserts precisely this, that for any primitive set, the Erdős sum of A is at most the Erdős sum of the primes. And so this is maybe notable because for various different ways of associating an entire infinite set to a single number, you could have various schemes, but for this particular assignment, the primes are coming out on top. The primes are maximal. And in fact, one can compute with some cleverness this infinite series 1 over p log p. So that's 1 over 2 log 2 plus 1 over 3 log 3 plus 1 over 5 log 5 and so on. And if you kind of naively try to calculate this, maybe it's a very slowly converging series. But there are some tricks that people like Henri Cohen and other people have done that actually you can get a very accurate calculation of what this constant is. And it's about 1.636. And so the conjecture of Erdős said that f of A, this Erdős sum, is at most about 1.63. And there was a number of works on this result. So in particular, in 1993, Erdős and Zhang, a different Zhang, had proved that the Erdős sum is at most 1.84 for any primitive set. And after a number of years, Pomerantz and I improved this bound to e to the gamma, where gamma is the Euler-Mascheroni constant. And one might think that if you're just trying to look at these Erdős sums, you could just directly compute these partial sums and then truncate at some large point. However, this kind of direct approach turns out to not work because the tail of the series, these series actually converge quite slowly. And in particular, for any choice of a truncation point that you might choose, there will be a primitive set, all of whose numbers are larger than x, and for which the contribution of this series is really kind of in this tail, so that the sum has a positive mass in this tail. And so this kind of direct approach, by just truncating an infinite series as a partial sum, doesn't really work. Another interesting idea that arose is a kind of local approach to this conjecture, in particular to split up your set according to the smallest prime factor in the integer. So in other words, for any prime p, we can consider all the subset of numbers a sub p where n has smallest prime factor equal to p. And then we can consider what's called an Erdős strong prime, saying that the Erdős sum at this subset a sub p is at most 1 over p log p. So this is saying that in some sense, the singleton set of just p is kind of maximal among all primitive a sub p's. And so in some sense, this is a local form of the conjecture. And if you could show that every prime were Erdős strong, then the primitive set conjecture would be true, namely that the sum of a over a, which splits up into these disjoint pieces over each a sub p, which corresponds to every number having a unique smallest prime factor, is at most the singleton at just p. And so f of a sub p is at most f of p. And if you sum up all the p's, then you get f of this primes, so this sum. So indeed, this is a very attractive approach to try to prove this conjecture. And in my doctoral thesis, I in particular proved this conjecture that the primes are maximizing the Erdős sum over any primitive set. And in particular, the method allowed to show that for any odd prime, that f of a sub p is at most f of the singleton of just p. So the methods allowed showing that kind of these local conjectures are true for any odd prime. And it remains kind of an open question whether or not this first prime p equals 2 is Erdős strong. Whether or not for any set of primitive set of even numbers, its Erdős sum is at most 1 over 2 log 2. And as often the case arises in number theory, one kind of handles the odd prime separately from the first prime p equals 2. And for this reason, people sometimes say that 2 is the kind of oddest prime of them all. So now we can maybe get to part of the focus of the talk, which is so-called Erdős problem 1196. And I'd phrase this as an asymptotic version of the primitive set conjecture in the case of large numbers. So let's unpack what this means. So in 1966, actually not just Erdős, but Erdős, Sarkozy, and Szemerédi, these kind of groups of legendary Hungarian mathematicians, they formulated a kind of version of the problem where they looked at integers all greater than x in the limit as x goes to infinity. And so they conjectured that for any primitive set of integers bigger than x, then its Erdős sum is at most 1 in the limit as x tends to infinity. So I think that number one, this is a very remarkable conjecture because by contrast with the original primitive set conjecture, you had some constant like 1.63 corresponding to this empirical sum over primes. Nevertheless, we get this very simple upper bound of just 1 itself arising in the kind of asymptotic version. And so, what? The specific of this conjecture. Yeah, we'll get to this. Okay, but it has a very probabilistic kind of conceptual interpretation. And what's very attractive about this problem is precisely that. And so in particular, the kind of methods for my thesis enabled a kind of upper bound about 1.4. There's about 1.399, getting in particular this factor of e to the gamma times pi over 4, marking kind of some partial progress using these methods. And so in particular, so in my thesis, I'd worked for 4 years on the problem of the original primitive set conjecture, and following this initial progress up to this point in 2026, that represented another kind of 3-4 years of continuing to work on this problem along with other problems. So I first want to emphasize with this conjecture, this limit of 1 has to be kind of sharp in the sense that, in particular, so this upper bound that I obtained of about 1.4, this number, e to the gamma times pi over 4, this is the kind of worst case of what you can get in the conjecture. And what they want is to actually get this number to be 1. And so you know that the lim sup that Erdős, Sarkozy, and Szemerédi are analyzing must lie somewhere in this interval between essentially 1 and 1.4. And their conjecture is asserting that there is an equality occurring at 1. And so this is because we can witness a lower bound by a family of primitive sets of numbers, all of which are large. So in particular, consider the numbers which have exactly k prime factors, including multiplicity. So in other words, we consider the product set of the primes with itself k times, the k-fold product set. And in particular, the smallest prime is 2. So the smallest element in this set is 2 to the k. So as k goes to infinity, all these numbers are going to be large. And it's a result of mine and others that in the limit as k goes to infinity, f of the primes, or f of these k almost primes, tend to 1. And this is very much related to why we get this number 1. There's a nice conceptual explanation. And in particular, if you want, there is a nice secondary term one can prove using kind of more refined methods. And you could actually identify what the coefficient is in the secondary term. You can get a tertiary term, And you could actually keep going if you want to. And in particular, it's interesting to note that this secondary term is negative, which is still kind of an interesting kind of conceptual point. Okay, so this was the state of play until this year, that we had this conjecture from the 1960s. We had some partial progress 3 or 4 years ago, and to my surprise, this conjecture was actually resolved in April. So after 60 years, we have a solution. And in particular, on April 13th, the amateur mathematician Liam Price posted this solution to the Erdős Problems website maintained by Tom Bloom, saying that GPT 5.4 Pro claims a solution along with a PDF and a kind of a attached kind of a chat log. And in particular, GPT ran autonomously on the problem for about an hour and a half, 80 minutes, producing raw output which looked like a candidate solution. And however, the draft was kind of written quite poorly. And maybe you might think of this as you have some student in a class, he has homework the next day, so he kind of scribbles quickly on a scratch pad. But maybe the student's actually kind of knows what's going on, but it's just very disorganized. And so it requires the maybe belief and forbearance of the teacher to actually take the effort to read and try to decipher what's going on. So this is exactly what I was tasked with. And so after, so the proof was only, or the candidate proof was only 4 pages long. And I was pretty skeptical given how old of a conjecture and a conjecture that I care about. However, but about an hour or so of deciphering this kind of initial draft, I kind of realized that there was an interesting idea here, and the draft actually contained a correct proof once cleaned up. And in most respects, the proof is actually quite similar to Erdős's kind of idea, kind of his initial kind of program that he put forward in the 1930s, but essentially to construct a measure to interpret anatomy of integers of the elements in a primitive set. However, there were some technical kind of clever introductions of, in particular, the von Mangoldt function when defining a new set of weights, so-called B sub x of n, which are rather, reasonably elementary to state, which I will in the next slide, but in particular appear quite counterintuitive relative to the previous work of Erdős and others. So in particular, for those of you who have taken an introductory analytic number theory course are familiar with the von Mangoldt function, which is defined on prime powers as log p whenever n is p to the k, and otherwise is defined as 0. And so for students who are learning about the von Mangoldt function for the first time, this appears maybe like an odd definition. Why would you introduce this? But it turns out this is really the kind of natural definition you'd want once you have in mind the kind of Riemann zeta function and trying to look at Dirichlet series, taking the maybe logarithmic derivative. So from the right perspective, it's actually quite a natural kind of choice to make. And in particular, there's a key identity that the von Mangoldt function satisfies. So lambda satisfies the sum over all kind of divisors of an integer n of lambda of q equals log of n. So this is one of the kind of first results that you prove in an analytic number theory course. And this kind of simple but key identity is equivalent to the unique factorization of n into prime powers. So in particular, this sum over lambda is going to be 0 unless q is a prime power by definition. And this identity just encodes a unique factorization. And so just as maybe similarly this kind of definition appears odd, but encodes some nice information, I just want to introduce this. Oh yeah, so I'll come back to this. But there is similarly a way in which the introduction of the von Mangoldt function and of these weights, b sub x of n, maybe appear a bit odd at the first kind of introduction, but actually from the right perspective turn out to naturally encode some nice information. Okay, let me return to this. Okay, so for context, so in all previous work on this problem and related works on primitive sets, Erdős had really kind of set the stage back in 1935 with his original paper using the following idea. So relate the sum 1 over n log n, so relate these Erdős sums to corresponding so-called Mertens products. So products over primes up to, in this case, the largest prime factor of n, p of n. So Mertens' theorem, so Mertens' third theorem, tells us that 1 over log n is growing like a constant times the product of p over up to n of 1 minus 1 over p. So we have this kind of nice factor that arises in many contexts in number theory. But in particular, so here p of n is the largest prime factor of n, and c is this constant of e to the minus e to the gamma. And the kind of nice idea here of Erdős was to kind of start from some kind of technical analytic function, this 1 over n log n, and then convert it into something that could be interpreted as probability, so that these kind of products can be interpreted as the probability of some event occurring. And the nice thing about probabilities of disjoint events is that they always sum to at most 1. And so we can actually give in one slide here just a very nice sketch of this proof of Erdős that f of a is bounded uniformly. And let's assume, in particular, that all the integers in our set are large. And just in one slide, we can kind of set out the entire proof. So we start out with our sum, our Erdős sum of 1 over a log a. And in particular, this is at most 1 over a log p of a. So 1 over the largest prime factor, p of a. And by Mertens' product theorem, there's some constant for which the log can be converted into this product of 1 over 1 minus 1 over p. But the point is that once we have it in this form, this expression of these products are identified precisely as the natural density of a particular set of integers. So namely, this set L sub a, which is so for any a, we define L sub a as the product b times a, where b are all numbers who have prime factors bigger than p of a. So in other words, we're looking at numbers where all the small primes are coming from a and all the big primes are coming from b. And so we can express this upper bound, this sum of products, as a sum of densities. So now we have a sum of densities, and so far we've done nothing assuming about the set A. But we know that the set must be primitive, so somehow the property of being primitive has to play some role here. And the role it plays is exactly, by a short argument, that any primitive A forces these sets L sub A to be disjoint. So if a set A is primitive, then these sets of multiples cannot collide. Perhaps this is a bit, so maybe this is obvious to look at, but in any event, it's only a few line proof. And now that we have this sum of densities of disjoint sets, this is equal to the density of the union of these sets. And so this is some set, and in particular, the density of some set is always going to be at most 1. And so you have this kind of sum of disjoint events, these disjoint probabilities will be at most 1. And so in particular, we get this bound of f of a being bounded by some constant times 1. And so this, just in one slide, is Erdős's argument, and it's very nice because it kind of casts the whole problem in a probabilistic language. And this really kind of set the tone for his work and many others' work looking at all these problems. And it's also worth remarking, maybe in hindsight, that Erdős's argument can also be equivalently formulated in the language of what's known as like sub-Markov chains, in this case for the Mertens weights. And in particular, that primitive sets, or these anti-chains, will hit the sub-Markov chain at most once. And so there's a completely equivalent language to formulate this. And also, so if you want to make further progress on this conjecture, you have to kind of make quantitative what these constants are and try to kind of refine them. And so in my thesis, I worked on refining the above relationship, in particular by the first step that was taken by replacing, that we replaced A itself by its largest prime factor. And so this will change the upper bound by a constant. And if you actually care about the constants, this is actually an important place to get the upper bound improved. So in particular, if A is a prime, nothing happens. But if A is composite, you actually get a loss here. And so this also starts to conceptually explain maybe why the primes are optimizing the whole Erdős sum, is because in this initial step, you don't have a loss if it's prime, but if it's composite, you do actually get some loss. And there's a lot of work to try to make that intuition more refined or kind of more rigorous. And one can kind of start to do so by looking at not just the first prime factor, but also the second largest prime factor. And one can give kind of more rigorous probability theoretic meaning to the anatomy of integers for each n in your set. And analogously, so this was something I was kind of working on for the past 3 to 4 years, was to extend this idea and iterate it to study the so-called joint distribution of the first j largest prime factors of an integer. And this kind of analysis works extremely well in the case of when A is exactly the set of k-almost primes, when it's the k-fold product set. And in this regime, this exact argument, kind of general iterated j times, allows to show this identity that the Erdős sums do tend to 1 in this special family. And so this kind of laid kind of some idea of how to generalize this. However, when you move beyond the special case of the family of k-almost primes to some arbitrary set, you get really some very complicated iterated integrals arising that satisfy general kind of mass constraints. And to this day, this kind of iterated integral optimization problem is still open and has not been resolved. However, the kind of point of emphasis I want to make is that the proof that was given by GPT 5.4 was essentially sidestepping the whole kind of difficulty that was kind of initiated by Erdős's kind of probabilistic viewpoint. And so one could kind of formulate is that by introducing these weights, these b sub x's, in terms of the von Mangoldt function, one could equivalently simulate a lot of the steps that are made in Erdős's argument that kind of look very odd on the face of it. But if you already have in mind Erdős's form of the proof, then you can see where GPT is like mimicking the same kinds of steps in probabilistic language. And so especially if you recast Erdős's proof in terms of these sub-Markov chains, then it's exactly essentially the same structure, the same form of proof. And in the particular implementation of the proof that GPT obtains is quite slick and reduces just to this key identity that we mentioned, that the sum of lambda over divisors of n is equal to log n. And so this exactly is something that cancels this log n squared in the denominator, and just you get 1 over n log n. And as I said before, it's very, I would say, kind of slick and perhaps not as conceptual unless you already had in mind kind of Erdős's original framework. Okay, and so this was a very nice graphic that was produced by Sebastian Bubeck using ChatGPT images. And so Sebastian is the kind of head of kind of team at OpenAI that does kind of AI for math. And he plugged in the proof that GPT generated and asked him to create a graphic. And so this is one of these very nice, beautiful proofs that's compact enough that you can actually express the whole proof in one slide. Assuming some basic identities, some elementary estimates like Merton's theorem and Trebuchev's estimates, and some basic kind of probability about Markov chains, then you can formulate the entire argument in just this one slide. So it's quite nice, and I encourage you to look this up on your own. But what's more is that once this initial proof was generated in just an hour and a half, it turned out this kind of general kind of formulation turns out to actually open up a number of other problems that kind of I'd been thinking about that are related in the area. So in particular, one thing to remark is that this construction actually not only resolved Erdős 1196, but also made it quantitative. So it gave an upper bound that not only tends to 0 as x goes to infinity, but also showed the quantitative error decaying like 1 over log x. So that was something in particular that wasn't even conjectured. Node made a conjecture. In fact, I think it'll also be interesting to note. Now, one could ask about, is this optimal, and try to refine it even further. But in particular, this was beyond kind of doing extra credit beyond what was asked of GPT. So another thing to remark is this notion of divisibility chains. So maybe it's kind of worth taking a step back and thinking about what is a primitive set. So remember, this is no number in the set divides another. And so from a maybe combinatorial formulation, this is what's known as an anti-chain for the kind of ordering of integers by the divisibility operation. So no two elements are comparable using divisibility. And as such, this kind of leads us naturally to dualize and think of the dual object, which is a chain. And so what does that mean of a chain is that any two elements are comparable using the divisibility operation. And so this reduces to the simple kind of object, which is just a sequence of integers, d1, d2, d3, and so on, such that each one divides the next one in the sequence. And so this divisibility chain is really the dual object to a primitive set. And the kind of classical theorem of Davenport and Erdős from the 1930s says that if you have any set of upper log density, so if a set is large enough in a technical sense, then your set must contain an infinite divisibility chain. So just kind of for boilerplate, recall the definition of log density, of upper log density, is the lim sup of this kind of reciprocal sum of n up to x, and then you kind of normalize by 1 over log x. And so this is saying kind of maybe what you can think of as like a general theme in combinatorics and mathematics is that if a set is large enough, then it must contain structure. So in this case, if a set is large enough as specified by the logarithmic density, then it must contain the structure of a divisibility chain. So maybe some people in the audience may be familiar with like Zamarati's theorem on arithmetic progressions. So this is maybe following a similar theme where if a set is large enough, if it has positive density, then it must contain arbitrarily long arithmetic progressions. And so that's an example of saying if a set is large, it must contain additive structure. And this is an example of a theorem that says if a set is large, it must contain multiplicative structure. So kind of a related kind of question, in the 1960s, Erdős, Sarkozy, and Zamarati, in their kind of host of papers, they conjectured a quantitative form of this Davenport-Erdős theorem of, if a set is large, it must contain infinite divisibility chains. And you can ask, how large are these, or how often do the kind of elements in this chain arise? And they conjectured, and so this is formulated in the precise sense of double logarithmic density, which they say seems to be more interesting for this context, that if a set has this density delta bigger than 0, then there is an infinite divisibility chain D growing. So if you truncate D, so it's an infinite set, and if you truncate it at Y, then it grows like delta times log Y. And this occurs infinitely often for infinite subsequence of Ys. And kind of also as a boilerplate, the double logarithmic density is the sum of 1 over n log n for n up to x, and normalized by 1 over log x. So this is where the kind of notion of log density arises. And notice that this series of 1 over n log n arises. It's very natural as the kind of derivative of the doubly iterated logarithm. And so they conjecture this bound, this lower bound of delta times log y. And in fact, in their work in 1996, they proved a lower bound that was off by a factor of e to the gamma. So e to the gamma also arises often in these kinds of problems. So they had delta over e to the gamma times log y. And so they wanted to know that could you actually get rid of this factor of e to the gamma? And in fact, this kind of new von Mangoldt chain method introduced by GPT also can be adapted to yield a proof of this Erdős problem 1217 by, and in fact, getting rid of this e to the gamma. And for similar reasons why one gets rid of a factor of e to the gamma in the primitive set conjecture. So I also want to maybe highlight another, what I view as a kind of remarkable result that in previous talks at CANT, I've given as one of these kind of open problems. This was a slide that previously said future directions. So here is a question. So if you're considering any primitive set and you ask about maximizing the sums f of a, what is the maximum? So Erdős conjectured that this was the primes. But now you can ask a related question. So if you throw out the primes and you just consider primitive sets of composite numbers, then what do you think the maximum should be? Maybe I'll pause and see if anyone has any ideas. Yeah, exactly. So these semi-primes, these numbers with exactly 2 prime factors. So if you're looking at numbers with at least 2 prime factors, then you should be optimized by numbers with exactly 2 prime factors. And so in particular, Banks and Martin, who are sometimes in the audience, conjectured, in fact, that this is the case. And they actually introduced this as a example of a much broader family of conjectures. In particular, if you take any k and any set of primes, then looking at primitive sets made up of at least k primes, and all of those primes are lying in your set Q, then the Erdős sum f of a is at most f of the k almost primes from Q. So this k-fold product set Q. So this is, in one fell swoop, a generalization along many directions for any number of prime factors, for any choice of primes. And so, yeah, so recall that Q to the k is this k-fold product set. And so this is what I would view kind of in the back of my mind is like this master theorem that is really governing a lot of these conjectures that we've been talking about. And this was kind of made explicit in a paper of Banks and Martin from 2013. So in particular, one of the predictions as a special case of their conjecture is that if you specialize to your set A being the kind of next set just being Q to the k plus 1, then it should be dominated by Q to the k. So in particular, as k increases, we should get this like chain of inequalities that we have like these nested kind of decreasing, monotonically decreasing sequence of Erdős sums. And so this is a very kind of beautiful kind of test case to try. However, it turned out that life or that kind of numbers were not as abiding. And so one thing to note is that already in 1993, Zhang proved maybe the first part of this, first step in this kind of special case by showing that the primes are maximizing the Erdős sums for any kind of almost primes, for any k. So the primes are maximizing. However, to my surprise, I found that actually the numbers with exactly 6 prime factors are minimizing Erdős sums for any k. And so this was number one, shock. And this was kind of further made a shock to me, and was made further precise in later work with Ofir Gordetsky and Modek Wang, in which we showed that so for any k large enough, so as k grows, we would have kind of Banks and Martin would predict that these sums would decrease monotonically, but we showed in fact that these sums are increasing monotonically for k large enough. However, if we throw out the first prime 2 and just consider Q to be the odd primes, then we recover monotonically decreasing sums. So the all kind of k-most primes versus odd k-most primes have opposite behavior. And so this was something that was particularly surprising. And in particular, it'd be nice to generalize this result from k large enough and quantify it. So numerically, it's been verified for k up to 30 also. So it'd be nice to have it maybe bridging the gap in between for someone in the audience. Okay, so we have this kind of formulation, and which kind of shows that the Banks and Martin conjecture is not true as formulated. So that was a kind of disproof. However, maybe kind of in the same philosophy of 2 being kind of a nuisance, we already saw that with earlier results. That kind of motivates a kind of odd version of the conjecture, where if you just restrict your numbers, or that your primes Q to not contain the first prime. So if you have an odd set of primes, then you should hope that, or you might hope that you could still recover the conjecture in this case. And so this is a conjecture that I formulated, that in the case of odd numbers, you should get this kind of nice hierarchy predicted by Banks and Martin. And what is remarkable is that the same kind of methods GPT developed with the von Mangoldt chain also yields a proof of this full odd version of the Banks-Martin conjecture. So in particular, for any k and for any set of odd primes, every primitive set of numbers with at least k prime factors, all coming from Q, are maximized by the Q most primes, the k most primes for Q. And so this is now a theorem. And also in particular, in the course of implementing this proof, you actually see why the even numbers break and what conditions are failed. And it kind of illuminates some of this prior confusion. And maybe taking a step back, so from my point of view, this was maybe one of these kind of master results that I was really kind of looking towards for a long time. And to maybe take a step back for context, this is because the definition of a primitive set is very simple. So just like a prime number, you have a very simple definition. And so with a simple definition, you can admit a lot of examples. And so it defines a very broad class of sets, and also admits many pathological examples. So we already kind of talked about Besikovich's counterexample, which was very pathological. And so this is a very broad class, but nevertheless, this kind of now result of Banks and Martin, odd Banks-Martin, asserts that this class has like a hierarchical structure. It has a kind of a grading to it in a very nice way with the k almost primes. And so I find that particularly beautiful. And maybe in the kind of last 5 minutes or so, I want to take a moment to maybe take a step back and highlight some broader themes that I think this result highlights. So one was maybe the discrepancy of how hard a problem was thought to be before, and then looking at the resulting output once you have a proof. So Erdős talked about these looking at proofs from the book. Maybe the proof is very short, but we can't read it, so we don't know which problems ahead of time are going to have nice proofs. So there are many other examples where a short argument, maybe it seems counterintuitive, can cut this Gordian knot. And so very notable examples include, so Terry Tao mentioned this example of the finite field Kakeya conjecture that was originally made progress on by Terry and by Jean Bourgain in a kind of a monotonic sequence of papers making partial progress, but then were of significant technical complexity, but then was kind of subverted by Dvir, who was at the time just a PhD student, and came up with this very nice argument with the polynomial method, and then had a lot of nice generalization to other topics. And there was another result more recently by Huang with the sensitivity conjecture that turned out to be a quite nice short proof. And so, not often, but sometimes you can get these problems which appear on the face of it quite difficult, but turn out to have a very nice proof when viewed from the right perspective. And another kind of maybe psychological phenomenon is this idea that after an initial kind of progress is made, then there's like this cascade of many other results. So this is an example when after the initial proof of this one problem was solved, then there was kind of 4 other problems. So we did 60. If you have like a plot of the, like a time series of how many problems were solved by this method, it goes 0, 0, 0 for 60 years. Then you get one after a 60-year wait, and then 4 days later you have, or then a few days later you have 4 subsequent conjectures. And so this plot is very very, very sharp. And so an example I like to think of is maybe the case like the 4-minute mile. So for a long time, this was considered to be something that was unbreakable, maybe in the 1900s, and then Roger Bannister broke it in one kind of attempt, and then right after that, there was a series of other runners that just broke right through it. So maybe part of it might have been psychological. So another thing, more recently, of kind of trying to reflect on the proof itself. So I would essentially view this GPT proof as being a very kind of slick argument that really kind of makes everything nice and short, maybe obscures some of the kind of conceptual formulation. And if you have the concept in your mind, then you can kind of reinterpret and kind of see why you would make these kind of decisions. And so maybe one of the analogies I like to think of what this proof has given is maybe goes along the lines of chess. So in chess, there are these kind of long history of players making opening moves, and it's a well-studied environment where all the top players really know essentially every starting move, and they maybe wait like a sequence of 10, 15 moves down the line for some interesting play to happen because everyone knows how things begin. But in the case of automation, when chess engines started getting good, they sometimes found alternate openings, and this kind of gave an opportunity for players to really kind of experiment and start to have things getting interesting again. And I would kind of describe this by analogy, like just as Erdős had really kind of set the formulation of how to think about these primitive sets since back to 1935, essentially, one could think of this kind of alternate formulation as being a elementary, though perhaps counterintuitive opening to a way to start looking at this kind of problem. And once that kind of opening is suggested, top players can then know how to work with that opening. But the main contribution is thinking of that kind of counterintuitive step in the first place. And so that was kind of maybe a psychological leap. So this is I think something interesting. And something I was also surprised about was some of the kind of maybe reaction of other people to this kind of problem. And I should also set the context is that in the past few months, so since April, there have been essentially 50 solutions to Erdős problems, which is, I think, unprecedented. So in total, there may be about 1,200 of these problems, at least on Tom Bloom's website, and 50 of them, or initially maybe, I think last year, there were a number of them that were kind of retrieved from old papers in the literature, which aren't really solving a problem, but kind of pointing people to previous generations. But in the past few months, there have been a wave of about 50 new solutions, which is definitely something to be reckoned with. But I was quite surprised when maybe some members of the public who weren't necessarily mathematicians were suggesting this is might be a move 37 for math, and my kind of response is that no, so this is not a move 37. And maybe what I would say is that more precisely, they're asking a question of there is a setting in Go where maybe about 10 years ago, machines played the best Go players in the world at this very old game and essentially beat the best humans. And so the question as posed is, was this an example of machines beating the best mathematicians? And one could say, at least my thought would be that once a machine can actually derive the Riemann hypothesis or solve, or at least solve these kind of very kind of deep open questions, or maybe even formulate a new definition or a new theory like the Langlands program, I think this might represent something like the kind of move 37 moment. And I thought about this question for a bit, and then I actually thought to myself, maybe there's a kind of way to subvert this, actually, because if you think about it, move 37, so this was a move made in game 2 of this championship match, of which the AlphaGo machine actually found this move that was extremely counterintuitive, and that all the experts thought that this was like a losing move, but later turned out to be a winning move. On the other hand, I think the kind of popular conception of move 37 itself is actually not what kind of public think about. And I think the move itself in isolation isn't really as interesting as the broader kind of scope of the kind of strategy that the machine was employing. So there was not just game 2, but there was a sequence of several games in which the machine beat Li Zidol multiple times, and only one of these moves had this kind of identifiable moment. But really, all the games had this characterization, which the machine was making these very calculated decisions about optimizing not just for points of stones, but also for momentum and opportunity, and was doing this kind of very rigorous cost-benefit analysis of trying to win by even the smallest margin, when a human player would decide to really try to take stones when they can to make things easier, and as a good heuristic. But this was maybe one kind of consequence of move 37 kind of arising, and I don't actually think move 37 is the move 37 of Go. So in that sense, maybe move 37 isn't as interesting as the broader strategy of AlphaGo employing this very broad kind of dynamic cost-benefit strategy. And so in that sense, I think we're very far away from that kind of analogy. But who's to say what will happen in 1 year from now? So that, I think you present.
Question for Darren?
Cool.
On the other application, where they might use conjecture that the average sum of those less than or equal to 1. Next question. It seems to be true. Oh, it's okay.
So say it again. I didn't hear the question. Mm-hmm.
Here plus theta bar. Might do conjecture in the earlier circle chart. Already conjecture that A is primitive set. All of the color is greater than X, and X is large, and the error sum is less than 1.
Yeah, so I think maybe the equivalent way is saying that you have like it's like the little o1 is like negative or some sense. Yeah, so I think that might be true. I don't know how to prove it, but I think that would be a good problem to introduce for the problem session.
Can I also ask something? So about the Banks-Martin conjecture for odd numbers. What if we remove some other number, not 2? So say, is it true for numbers non-divisible by 3?
Yeah. So number 1, that's a good question. Number 2, for the record, Mel wants you to identify yourself.
What?
Well, who's asking the question?
Kalminin.
Okay. Yeah. So I think it's an interesting question. I think the methods might be able to work on an ad hoc basis if like you're specifically have a passion about the prime 3. But in terms of getting a general characterization, I think it might be possible, but it's not immediately direct.
So maybe in some sense, the prime number 2 is somehow worse than the 3. So if you allow 2, then you should prohibit something else, not just 3 or 5 or something else.
Yeah. So if you prohibit 2 and anything else, then it works. Yeah. So in some sense, we know that 2 is the main issue. But if you're specifically interested in 3, omitting 3 but nothing else, then you have to do, or at least the direct approach, the naive approach would be to compare how poorly 2 is doing with the gains you get from the odd primes besides 3. And so yeah, right now it seems to be kind of an ad hoc problem, but I'd be interested to talk more.
Thank you.
So would your problem still be open if ChatGPT hadn't spent 80 minutes on it?
Yeah, definitely. I mean, an interesting thing to say is that if you were given one sentence. If I were given one sentence, maybe if Erdos was given one sentence back in the 60s of saying, try this approach with these von Mangoldt weights, then he could go and implement that proof. But just coming up with this one sentence, that just seems like an odd construction on the face of it, I think is the main contribution.
Okay. And Jared again. And then our next talk at 4 o'clock will be something akin to